After we learned about heat and work and basically transferring energy between the system and the environment, we will today discuss more in detail work. Specifically, we will learn how to calculate work for various situations. That means how to integrate an applied force over a distance and to integrate applied pressures over volume changes. And we will understand the relationship between forces and potential energies. The latter will actually allow us to calculate work for more non-trivial cases where the force is not constant. In all of this, be ready for integrations. If this is something that you're not yet very comfortable with because it's been a long time ago, be sure that you review them as quickly as possible. This is something that you will need more and more in the coming lectures. So let's begin with something straightforward out of the experience world from every day. Lifting weights. So what is work? Work is energy consumed while working against the force. And if you look at that weight, well, there's a force that pulls it down to the ground. This is the gravitational force, call it here Fg. If you want to keep the weight where it is right now, basically hanging in the air, we have to apply a force, which I call F prime, which is exactly the opposite. So it points exactly the opposite direction. And if I add both forces, it's equaling to 0. So this is one of the simplest cases of work because the force that is basically acting the weight, pulling it down, the force that we have to apply to at least keep it level, and maybe we need a little bit more to actually keep the thing moving, but we can do it as slowly as we want. This is constant. This force, the gravitational force, is constant, and the force we need to apply to basically move it is also constant. The gravitational force is easy to calculate. That is basically acting on this barbell and pulling it down. Fg is m, which is the mass of that barbell, times minus g. And g is the gravitational acceleration, 9.81 meters per second squared. I'm using a minus here to indicate the direction that it's pulling it down. If we want to lift that weight, we have to apply the force F prime, which is exactly the opposite of that. This is a weight with this minimum requirement to keep it level, and if we basically move the barbell up as slowly as we can, then this is basically the minimum force that you have to apply for that. And this is the one that is relevant for the amount of work that we are performing. So what happens if we lift the weight from an initial height, h0, 0 meters, to h1, 2 meters? This integral will basically haunt us several times. So this is the work and how it is actually defined in terms of force. So this is the force that is applied, F prime, which is the opposite to the gravitational force. And it is acting over the distance h, or in this case a height difference. And we have to integrate that. So we have to integrate that from the initial height to the final height. Here, as I said, this is one of the simple cases because the force F prime that we need is just the opposite of the gravitational force, and that is constant. That is always m times minus g. If it is constant, then in this integral, we don't have to actually integrate that in a particular way because it's just a constant number. We can put that in front of the integral. And this integral over here, well, that is becoming very simple now because it's just dh. And we know that we basically calculate the integral of dx, something that you might be more familiar with, and this is simply x. So this becomes simply h, but we have two boundaries. We have h0 and h1, so we have to integrate it in these boundaries, and that is then simply h1 minus h0. You can also call delta h. So the work that we are performing in the end, because of the simple integral, is f prime times delta h, or if we plug in for f prime what it actually is, this is m times g. The work that we are performing is m times g times delta h. Now if we want to plug in the actual numbers, again, units are important. So the mass m of our barbell is 45 pounds, as you can see here. Pounds is not the SI unit for mass, so we have to convert that. This is the conversion factor into kilograms, so this is 0.454 kilograms per pound. And if we multiply that, we get 20.4 kilograms for the mass of that barbell. So the work is 20.4 kilograms times the gravitational constant times the meters. This equation, just plugging in the numbers, and this is 400 joules. 400 joules sounds like a lot. It's a significant amount of energy that we have to invest to lift that barbell from the ground 2 meters high. Well, the frustrating part of all that, because this sounds like a significant workout, well, the caloric value of one gummy bear, essentially the energy which is stored within one gummy bear, is 35,000 joules, which sounds crazy, but what is a joule? Well, 35,000 joules is 35 kilojoules, and 35 kilojoules, if we convert that into kilocalories, which in slang is very often called calories, but it's actually kilocalorie, is 8.4 kilocalories. So you can calculate for yourself how often you basically have to lift that barbell in order to burn the energy of one single gummy bear. Many, many times. That is then already a serious workout just for one gummy bear. As I mentioned before, this equation is basically what determines work. There's always a force that is acting on something and is acting on something over a distance. If you will just apply the force without the barbell moving, if you just basically keep it level, it may sound like we're performing work, but we're not actually performing any work, because as long as the barbell is not moving, there is no work performed. Only if we move it from one particular place, in this case from one particular height to another height, if we change it, then we are actually performing work. Just keeping something there is not performing work. Now let's talk about a different type of system where work is performed. We already learned about systems that are mechanically coupled to their environment. For example, via frictionless piston, like these ones over here. Look at the system. Initially, we might have a volume V0, which is indicated over here. This is essentially the piston that has currently position H0. On the cross-section, or the area of that piston, is indicated as A, and the atmospheric pressure, in this case, the external pressure, is pushing on that. And if a piston wants to expand, if a gas in the piston wants to expand, it has to push the piston up against that pressure, change its position from H0 to H1 by a value of delta H, and then has a new volume V1. So what is the force against which the work is carried out in that case? As indicated here, it's the external pressure, the pressure of the atmosphere, for example, that is pushing on the piston, and our system has to work against that. So that force can be simply calculated, because we remember that the pressure is nothing else but a force divided by an area. We actually know exactly what this area is. So the force is nothing else but the pressure times that area, and we get a force again. So this is basically the force that is exerted by the atmospheric pressure on that piston, and we are working against that, and we're trying to expand the system inside of the piston. The external pressure is the atmospheric pressure. The atmosphere doesn't really care if that piston expands or not. The atmospheric pressure is going to be constant, which makes things, again, quite simple. So we learned that the work is not performed by the force against which we are working, by the opposite, by the applied force. We call it again F prime, and it's exactly the opposite. It's minus F. So this is now minus P, the external pressure, times A. And then we can perform the normal integration, just like before. We have our integral from the first initial position of the piston H0 to the final position H1. The force we have to use is F prime, and that is minus, put a minus here in front, the pressure times the area times dH. Now the volume change itself, delta V, actually is nothing else but, when we remember simple geometry, the area of that piston, basically how wide that piston is, times delta H, times the change in the position of that piston. This is the change in the volume of that thing. For infinitesimally small changes of delta H, so dH, we get infinitesimally small changes of the volume of the system. This is dV. And when we look at that, this is simply A times dH. This is already what we find in this equation up here. So we can express this integral also differently, not as a function of the piston position, but as a function of the volume of our system. And that looks like that. This is the same equation, and it means exactly the same thing, but it's now written slightly differently. So now the work is minus the pressure, and we integrate over the volume from V0 to V1. Since the external pressure is constant, And this is essentially what we work against. You can put the pressure in front of the integral, integrate over this change in volume, which is delta V, and this is our work, minus external pressure times the change in volume. Now the nice thing about that is that it actually works for any kind of geometry. It doesn't have to be a piston like this. It can be a balloon that expands. As long as the pressure it works against is constant, you can use the same equation. In general sense, we now learned that work is basically work performed by a force over something that is moving, something that is changing. So let's look at some less trivial cases where the force is not necessarily constant. Energy is consumed while working against a force. This is what work is. So here we now have a system where the force is not constant. It's actually changing while we are performing work. It's called a spring or a harmonic oscillator, depending on what you're used to. And this is basically what the system looks like. Here it is at rest. So the spring here is basically now in its optimum position. This particle is where it wants to be. If we pull on that, it's basically the spring is charged. It will pull the particle back. If we push it in the other direction, if we compress the spring a little bit, it will push it back. So here this is basically the minimum energy position of that spring. The force that is exerted on that particle if we pull it away from the minimum, or if we push it basically further close to that wall here, well, that force can be expressed as minus k times x. This is Hooke's law. This is the force exerted by the spring. K is a so-called force constant of that spring. Now, if we have our particle here at the initial position x0, and we want to move it to the final position that we just call A, and we have to apply the force. Well, it's the opposite of the force that is basically pushing on or pulling on that particle, so it's exactly the opposite of that. So it's the opposite of minus kx, and that is simply f prime, that will be kx in the end. This is our standard integral. We have to integrate from the initial position of a particle 0 to the final position that we just call A. The force that we have to apply is f prime, the opposite of the force exerted by the spring. We plug that in, we get kx dx, and we integrate from 0 to a. So this is pretty simple. Kx is now a relatively simple integral. The force is not constant because it's itself proportional to x. So this is changing while the particle is moving, while we're pulling on it. But it's a simple integral. Kx integrated is 1/2 kx squared. And we have to integrate that in the limits from x equals 0 and x equals to a. So we have to look at that difference over here, and that is simply 1/2 ka squared. If we look at the potential energy of its system, if you know something about harmonic oscillators and springs, then you might have seen this before, the potential energy of its system is described by this parabola. And the parabola is essentially 1/2 kx squared. If we look at the positions minus a and plus a, so this is essentially where we pulled our particle to, or we pushed it to that's also possible, then the potential energy of the system will be 1/2 ka squared, exactly as we calculated it here. Because in this case, we were not transferring any heat into that system, we were simply applying work, and we were changing the potential energy of the system. This is exactly what we see here. So this amount of work that we applied is going into the potential energy of its system. We change the potential energy from 0 before to 1/2 ka squared. So the harmonic potential, or the potential energy of this harmonic oscillator is 1/2 kx squared. A was the particular position that we used, but in a general sense it can be written as a function of x, so this is 1/2 kx squared. What is the force that is acting on the particle in harmonic potential? We already know that, it is minus kx, but can we be a little bit more precise about that, and especially how it is related to potential energy? This is going to be important. If the particle position is x equals 0, then the force is 0. You can see that here. You can see it in particular because at x equals 0, we sit here right in the middle, and this is where the particle is happy, or the spring is happy. No force is exerted. This is exactly where everything wants to be. If the particle position is larger than 0, we pull the particle to its positive numbers, positive values, then the force of a spring will pull it back towards the minimum. So the force will point into that direction, and this direction we basically call negative relative to x. So it's a negative force, pushing it back or pulling it back towards the minimum. If the particle position is less than 0, so it's now on this side, now the force points in the opposite direction because the spring pushes it back towards the minimum position. Now the force is positive. So these are all qualitative statements, and they make sense, and we look at this graph and it also makes sense because we always, or the spring always wants to push the particle or pull the particle towards the minimum energy position. But can we do that quantitatively? How is that exactly related in a quantitative way? Well, the magnitude of a force is equal to the slope or the steepness of a potential. More specifically, the steepness of that potential, but this is the derivative. We know that. We've learned about that before. And the force itself is the negative of that derivative. So it's not just the derivative, it's minus that. So for this potential energy, which is 1/2 kx squared, the derivative of that is, well, it's the derivative of 1/2 kx squared, that's kx, and the force will be minus kx. And this is exactly what we started with. This is Hooke's law again. And this is general. This is absolutely general. A force is nothing else but a negative derivative of a potential. So keep that in mind. That's something that plays a big role essentially everywhere where work is applied or forces play a role. This is an absolutely general definition of a force. It is a negative derivative of a potential energy. What that potential energy looks like depends on the system. In this case, it's a simple harmonic oscillator. In molecules, that's usually more complicated. And this is essentially what we're going to look at now. We're not going to look at forces inside of a molecule, but forces between molecules. We look at this general form of a potential energy curve. We already saw this. This is essentially a Lennard-Jones potential between molecules, for example, in the gas, or molecules that don't form a chemical bond and they don't have dipoles, they don't have electrostatic interactions, but they basically have these weak London dispersion interactions that push and pull them together to some degree. It's not a very strong energy, as we can see here in comparison to the thermal energy RT. But if they get too close to each other, there's a repulsion because of the Pauli exclusion. Now let's look at that. So this is the potential energy curve. Then we can write out what the force is. The force is nothing else but the negative derivative of that potential energy. This is the force that would be acting on these atoms, either pulling them together or pulling them apart. Pulling them together or pushing them apart. Sorry about that. So if the position r of the particles, this is the distance between the particles essentially. If this is here, then the slope of potential energy is negative. We see that if you go from small numbers of r to larger numbers of r, the energy goes down, so the slope is negative. And if the slope is negative, then the force must be positive. The positive force means you're pushing into this direction, so larger r, and that means repulsion. This is a force that pushes the particles apart. Now, if the particles are sitting right here, in the minimum of a potential, then the slope is exactly 0. This is why it is the minimum of a potential. And if the slope is 0, that means the force is 0 as well. Now, if the particles have a distance which is in this range, well, now the slope is positive. If we go to larger distances, then the energy increases, and that means that the slope is positive and the force is negative. Negative force means it's pointing in this direction, so towards smaller r, and this is attractive. If you pull the particles very, very far apart, basically where the potential becomes 0 and at some point also the slope becomes 0, then the force is 0 again. So if they're far apart from each other, they don't see each other, there's no force between them. This is the minimum potential energy, so this is the position where the molecules are in the energy minimum, as we learned before. This is the energy, the potential energy at that minimum, so this is in this case a little bit below 1 kilojoules per mole, but we don't have to worry about that number, just that we know that this is the potential energy evaluated at that minimum. And now let's think about how much work is needed to pull two interacting atoms apart. You again, just like before, we have an initial distance between particles. This is with our minimum, so right here. This is where we start. And now as a final distance, we basically use infinity. So the particles are very, very, very far apart from each other. So first we begin here, and then we pull them apart to an infinite distance. How much work do we have to invest in order to do that? Well, we have to apply the force F prime. And this force F prime is nothing else but the opposite of the force that is exerted by this potential, so it's the negative of that force. Now this is again our standard equation that we have to use all the time. We have to integrate over the applied force F prime, which is the negative of the force that is exerted by the potential. We plug everything in, then well, F prime is a negative of the force. The force itself is a negative derivative of potential energy. That means that F prime itself is simply the derivative of potential energy. But we are taking the derivative of potential with respect to dr, and then we integrate over dr. What does that mean? Well, it's already written here. There's nothing else, but this is written the same way. It's just different symbols that we might be more familiar with. We have a function f of x that we take the derivative of with respect to dx, integrate over dx again. We get simply the function f of x, just like what you see here. So we get simply our potential energy, but we have been integrating over the limits from r minimum to r maximum. So we have to plug that in. And if we do that, we get the potential energy at the maximum distance, infinity as we chose, minus the potential energy at the minimum distance, which is where we started. The first one, you can see that here, the potential energy becomes essentially 0, minus potential energy in the minimum. This is simply minus the energy of the potential minimum. And if you look at that, this is a negative number, minus 1 kilojoules per mole, and minus that is plus 1 kilojoules per mole. So this is, we don't really need the numbers, this is more general. So if we pull the particles apart, sitting over here, what we actually do is the work that we apply is a change of the potential energy that we see here. You get a very similar result for a harmonic oscillator, that we have work what was applied as nothing else but the change in potential energy. And this is what you see here for the more general case and for an interaction potential between molecules. So what we learned today is how to calculate work for various situations. Macroscopic cases as well as microscopic cases, we learned that we have to integrate applied force over distances. We saw that we can do, analogously to that, we can also integrate the pressure that is applied to something over a volume change. That also gives us work. We understood the relationship between forces and potential energies. Essentially, forces are nothing else but derivatives of potential energy, specifically the negative derivative of a potential energy. And we learned how to calculate the work for non-constant forces. So the work that is carried out by non-constant forces or against non-constant forces, depending on how you formulate it. So this involved a lot of integration, a lot of math, and a lot of mathematical symbols that you might not have seen for a long time. There will be more of that. So if this gives you trouble, then review this lecture carefully once more and make sure that you're comfortable with all the symbols of all these integrations before we move on to more complicated things.